tomorrow and day after, right? Okay. So let's start. You know, there are many ways of viewing algebra and geometry and so on. But one way of thinking of algebra is that it's about laws of composition. So what is a law of composition? You have some set E, and a mapping from E cross E to E is called a law of composition. More precisely, it's an internal law of composition. Internal means that it's taking two elements of E itself, combining them to form a third element. So this operation of combining two elements to produce a third element of the set E is sometimes written as plus, in which case it's called addition. Sometimes it's written as cross, in which case it's called multiplication. So you have x cross y, or it's also sometimes written as a dot, x dot y or x point y, where this dot also stands for multiplication. So you say that this law is written additively if you denote it by plus, and it's written multiplicatively if you denote it by a cross or a dot. So that is an internal law of composition on some set E. But if your set E is there, they can be what are called external laws of composition. So for that, you have an auxiliary set, omega. This letter here is omega. When I point at things, can you see those things? Dr. Gupta?
Yes, sir.
Okay. So when my pointer is there somewhere, I hope you can see what I'm pointing at. So an external law of composition is something which takes an element of omega, makes it operate on an element of E, and gives you back an element of E. So this external law or this operation is sometimes written as alpha dot x, where alpha is in omega and x is in E. Sometimes it's also written as x to the power alpha, where alpha may be written to the left or to the right. So you also use this exponential notation sometimes. Okay, so these are two very basic things, and on a given set, you might have not just one, but many internal laws of composition and some external laws of composition. And these external laws themselves might be from sets which themselves have some internal laws of composition. Okay, so this might sound very abstract, but it's all very simple, and it will become clear when we come to some examples. Okay, so what I've said till now is something very simple. An internal law of composition on a set E is just a map from E cross E to E. An external law of composition on E with operators in omega is a map from omega cross X cross E, I'm calling the set E, to E. Okay, so, okay. Now there are some other words which you might, okay, yeah. So now there's this notion of categories, which we are not going to use much, but I just want to say that many of the things that we are going to come across are going to be categories. I don't want to make that precise, but categories, the basic example of categories are, for example, the category of all sets and mappings between these sets. Another example is here on the left. These are called pointed sets and pointed mappings. What is a pointed set? It is just a set with one element in that set which is sort of distinguished. One chosen element. So it can be thought of as pairs, E comma star, where star is an element of E. Okay? And if you have two pointed sets, E and E prime, and their special elements are star E and star E prime, then a mapping from E to E prime will be called a pointed mapping if it takes the special point of E to the special point of E prime. If f of star E is equal to star E prime, right? So that's a very simple concept. I hope everybody knows what mappings are, right? I'm assuming that everybody knows what mappings are. So these are sets with some special elements. For example, the empty set cannot be here because every set here in this category has to have one element which is sort of distinguished. And mappings should take that special element to the special element. Another thing which we can imagine is you take the sets and mappings, but now on each set you put a law of composition. So these are pairs consisting of a set M and a law of composition mu M. What is mu M? It's a map from M cross M to M. Okay? And such pairs will be called magmas. So a magma is just a set together with a law of composition. Then you have mappings between magmas, or they could be they're sometimes called morphisms or homomorphisms even. So what is a morphism between magmas? It's a mapping from M to M prime. If M and M prime are two magmas, and mu M and mu M prime are the laws of composition of these two magmas, then a morphism of magmas from M to M prime is a mapping F from M to M prime, such that whenever I have two elements X and Y of M, and I compose them in M using the law of composition mu M, and take the image under F of this composite, what I get is the composite of f of x and f of y. Sometimes you express this property by saying that f respects the laws of composition of the two magmas. If this law of composition had been written as plus additively, then this mu m of xy would have been x plus y. And this requirement for it to be a morphism of magmas would be written f of x plus y is equal to f of x plus f of y, if both the laws of composition in M and M prime are written additively. Okay? So from simple sets and their mappings, we have on the one hand pointed sets and pointed mappings, and on the other hand we have magmas and their morphisms. Now you can combine these two things. You can have what I'll call a pointed magma or a unital magma. So it's a set E together with a special element star of E, together with a special law of composition omega E, but there's some relation between this star and omega and this mu. This is not omega, right? I must have mistakenly said omega. This is mu. So the law of composition is mu, and there's some relation between this special element star and the law of composition mu, which is that when I compose any element x, an arbitrary element x, with star, I get back x, whether I compose it on the left or on the right. So this is expressed by saying that x is a neutral element. This star, not X. Star is a neutral element for the law of composition mu, or it's a unit element. Okay? So this is a very simple concept. You start with sets and their mappings. You have a distinguished element in the set, then it's called a pointed set. If you have a law of composition on the set, it's called a magma. Now, when both these things are there, and they are compatible in this sense, the star is a neutral element for this law of composition, then what you have is a unital magma or a pointed magma. Okay? Now let's come to a condition on a law of composition which is very, very common. Many laws of composition satisfy this condition. It's called associativity. So if you write your law of composition additively as plus, then associativity just means that when I add X to the sum of Y and Z, I get the same thing as when I add Z to the sum of X and Y. Notice that the order of the elements has not changed. X, Y, Z, X, Y, Z. It's only the way the brackets have been put which indicate which operation, which of the pluses is performed first. On the left-hand side, yeah, why did I hear myself? But it's okay. Is that fine? Yeah. On the left-hand side, you are adding Y and Z first, and then adding X to it, X to the result on the left. On the right-hand side, you are adding X and Y first, and then adding Z to the result on the right. And these two operations should give you the same result for all X, Y, and Z in the set E. Then you say that this law of composition is associative. Similarly, if the law of composition is written multiplicatively, then this associativity condition will be written as X times the product of Y and Z is the same as the product of X and Y times Z. The order of the elements remains the same. It's only the bracketing which is different on the left and on the right. And if you get the same result, no matter where you put the brackets, the law is associative. Okay? Now, here, so if you have a unital magma, which is associative, in other words, an associative unital magma, E, where the unit element is 1 and the law of composition is dot, then you say that it's a monoid. Okay? A monoid is a very simple concept. It's just a set with a law of composition and a special element. The law of composition has to be associative, and the special element has to be a unit for that law of composition. Okay? So such things arise very naturally in nature all the time. So the basic example of a monoid is the monoid n of natural numbers. So natural numbers are 0, 1, 2, and so on, written in red over here. So this is a monoid under addition. Why is it a monoid? Because addition is associative, and the special element is this 0. When you add 0 to anything, you get back the same thing. You don't change the thing. And similarly, you have this monoid n star under multiplication. It consists of all natural numbers strictly greater than 0. So 1, 2, 3, and so on. If you multiply 2 of them, you get a third one. This multiplication is associative, and 1 is a neutral element or unit element for multiplication. You multiply anything by 1, you get back the same thing. Okay? So that's one. These are two basic examples, n and n star. And here is a more general example. You take any set S and take E to the set of all mappings from S to S. Okay? So these are all arbitrary mappings. There's a special mapping from S to S, which is the identity mapping. What does it take an element of S to? It takes that element to itself. Little x in S is being taken by this identity map to the same little x. And how do you compose two mappings? That you already know. These are mappings. So if you have a map from X to Y and a map from Y to Z, then you can compose and get a map from X to Z. Here you have a map from S to S and another map from S to S. Then of course you can compose them to get a map from S to S, right? This composition of mappings is associative. That is very easy to verify. Okay, so the set of all mappings from S to S is a monoid because it has an associative law of composition for which this special element, the identity map, is a unit element. That's one. So now we have seen 3 examples of monoids, and this one is actually infinitely many examples. There's one for every set S. There's this concept of a morphism of monoids. So this is a mapping from E to E. It should take the special element E1 of E1 to the special element E2 of E2. So that it's written here. It should take E1 to E2, and it should take the product of X and Y to the product of UX and UY. U of the product should be the product of the U's of X and Y, right? So that is the condition for it to be a morphism of monoids. Okay? So for example, now you have all these concepts and you can try to see, are there any morphisms from this N to this E, or this N to this N star, from this N star to this N, from this N star to this E. You can try to figure out what are all the morphisms between these monoids, just in order to understand what the meaning of these words is. Okay? So let me just stop here for 1 minute and ask if there are any questions which anybody has. Are there any questions? Can you all hear me?
Yes, sir. I have a question, sir.
Yes, tell me.
Sir, is there a particular formula to compute the number of morphism on different monoids?
Yes.
How we compute the total number of morphism on a particular monoid to monoid?
No, I didn't give any formula for computing the total number of.
If there is any formula.
Well, exactly. So from this N, so it's a nice exercise to show that given any monoid E and an element little x of E, there is a unique morphism from this monoid N to that monoid E, taking this 1 to that x. Okay, so this is an exercise which I should have written, and part of what your one of the ways to verify whether you have understood these concepts is to check that whenever you are given a monoid E and an element little x of that monoid E, there's a unique morphism from the monoid N of natural numbers to the monoid E, which takes 1 to x. Okay?
Okay.
So there's a unique morphism satisfying this condition. Now let's come to one of the most basic notions in all of mathematics, which is that of a group. Okay. Now this notion was introduced, as you might know, by somebody called C.S.Dalawat. He was a young French mathematician who lived in the beginning of the 19th century. And when he was some 16, 17 years old, he came up with this concept of a group, which has ever since, not immediately after Dalawat, but after a few years, 10 years, 20 years after his death, it became one of the most important concepts in mathematics, and it continues to be a central concept. So what is a group? So it's a monoid which has some special property. It's a monoid M with a special, the neutral element I'll call it, or unit element as some people call it, and some law of composition dot, but it should have some special property. The property is that all elements of this monoid should be invertible. Now, what does it mean for an element of a monoid to be invertible? So if X is called invertible, if there is some Y in M, such that when I multiply X and Y, I get the special element, the neutral element E. And I get the neutral element even when I multiply Y and X. XY should be equal to E, and YX should also be equal to E. If every element X has some element Y such that this holds, then this Y has to be unique. That's one of the things you can check very easily. And if it exists, it's called X inverse. If it exists, it's unique, but it doesn't always exist. For example, in our previous thing, this element 1 itself in the monoid N doesn't have an inverse. Here, the law of composition is addition, so the inverse would be written minus X instead of X to the power minus 1. It would be, the inverse of 1 would be written minus 1. It would be an element with the property that when you add it to 1, you get 0. But there's no element in N which has that property. So this element 1 is not invertible, 2 is not invertible, 0 is invertible in this sense, in the additive sense. And what is its inverse? It's 0 itself, because when you add 0 to 0, you get 0. Similarly, here in N star, no element is invertible except 1 itself, whose inverse is 1. In this monoid E of all mappings from S to S, the only elements which are invertible are the bijections. They are called permutations of S. So if your mapping fails to be injective or fails to be surjective, then it's not invertible. It has to be both injective and surjective for it to be invertible in this monoid of all mappings from S to S. So does everybody know what it means for a mapping to be injective or surjective or bijective? Yes or no?
Yes, sir.
Okay, very good. So everybody knows what these words mean. So we can continue. Now, if X is invertible, I denote its inverse by X inverse. This X inverse is always invertible, and the inverse of X inverse is X. Again, these are not things which are obvious, of course. They need a little bit of checking. So this one can be checked by just multiplying them together to see, these things basically follow from the definitions. Similarly, if you have a product and each of the elements is invertible, then this product is invertible and its inverse is the inverse of Y times the inverse of x. It's not the inverse of x times the inverse of y. It's not that. The order gets reversed. xy whole inverse is y inverse times x inverse. Okay, this is also very easy to check. So if you have a morphism of arbitrary monoids, it will take an invertible element to an invertible element. And I should have said, that's what I've said. The image of the inverse of x is actually the inverse of the image of x. Okay? So a group is a monoid in which every element is invertible. Which is to say, it's a set together with the law of composition and a special element. The law of composition should be associative. The special element should be a neutral element for that law of composition. And every element should have an inverse for that law of composition. That's today's definition. This is not how Dalawat defined it. He was working more with permutations. So for him, the basic example would have been the set of all permutations of a set X. This is what I've already mentioned a little while ago, that you have the monoid of all mappings from X to X, and the bijective mappings, also called permutations, are the invertible elements of that monoid. So these invertible elements themselves, under that, they are stable under composition. That's here. The product, if each of x and y is invertible, then so is their product. In other words, all permutations of any set X form a group, and this is called the symmetric group of X, and it's denoted S of X. This S, this letter is S, is a German way of writing S. Okay. Now we come to commutativity. So that's also something which many laws of composition satisfy, and it just means that the composite of x and y is the same as the composite of y and x. In other words, the order doesn't matter. The order in which I compose x and y doesn't matter. I get the same result. If it's addition, then the commutativity condition is x plus y equals y plus x. If you're writing your law of composition multiplicatively, then this commutativity condition is written xy equals yx. Okay? So you get a commutative notion of a commutative group. So it's just a group in which the law of a composition happens to be commutative. It's already associative, as in every group, or as in every monoid, in fact. But a commutative group is one in which the law of composition is also commutative. An example would be, if you take a group and take a set S, then the set of all mappings from S to G, the G to the power S denotes the set of all mappings from S to G. That becomes a group again. How do you multiply two elements of this set of mappings? If I have two mappings F and G, their product is another mapping, and the value of that mapping at little s and of an element of capital S is the product of the elements F of S and G of S in the group G. So that is sort of the product of S many copies of the group G. If the group G is commutative, then this set of all mappings from S to G, which is a group, is also commutative. So before I come to the next concept, I need to recall what a subgroup is. So a subgroup is a subset of G. If G is a group, then a subgroup is a subset which contains the special element E, the unit element. And if it contains two elements, X and Y, then it also contains their product, XY. And if it contains an element X, also contains its inverse. That's what a subgroup is. Now, when I have two commutative groups, G and H, okay, then I have the set of all morphisms from G to H. I defined this notion of morphisms for monoids, and it's the same for groups. And that set of morphisms, in particular, is a subset of the set of all mappings from G to H. A morphism from G to H is, after all, a mapping satisfying some additional property. So it's this thing here is a subset of the set of all mappings from G to H. And as I said, the set of all mappings from some set to a group is itself a group. So this thing on the right-hand side is a group, and this thing on the left-hand side can be verified to be a subgroup. That's why I defined the notion of a subgroup here. So you have this subgroup. Now let's consider a special case when G is equal to H. In this case, the set of all mappings from G to G is also denoted end-G. And a mapping from G to G, which is a group homomorphism, is also called an endomorphism of the group G. That's why it's written end-G. So it becomes a group for addition. Addition being the law of composition in the group G. But now something special happens. When the group G is commutative, the group of all endomorphisms has another law of composition, which is you can take two endomorphisms of G and compose them to get a third endomorphism. So now this set NG has two laws of composition, addition coming from the law of composition in the group G, and composition, which is just the composition of all mappings of sets, right? And these two laws of composition are related to each other by these two identities. So sometimes this is expressed by saying that one of them is distributive over the other. I forget which one. Maybe it's multiplication, which is distributive over addition or something. Anyway, what it amounts to is this identity, and this identity is easy to verify because to evaluate this mapping on the left at some point X of the group G is this by definition, which is this, which is this, which gives you this identity. Okay, so all this was there to say that when you have a commutative group G written additively, the set of all endomorphisms of that group G has two laws of composition, addition and composition. And of course, it has two special elements, the zero element, which is a zero mapping, which sends everything to zero. And it has an identity, which is the identity mapping, sending an element X to itself for every X. So this was there to introduce the notion of a ring. So a ring is just a set A together with two laws of composition plus n times and two special elements 0 and 1 such that A plus 0 is a commutative group, okay, called the additive group of the ring A. And A times 1 is a monoid called the multiplicative monoid of the ring A. I'm not asking it to be a group, right? So some of the elements may not be invertible. In any case, I want these two laws to be compatible with each other, exactly in this way, in which one is distributive over the others. So what that means is, I take an element X and this left multiplication by an arbitrary element This is the left multiplication by the element A. X is being sent to A times X. So left multiplication by an arbitrary element A and right multiplication by an arbitrary element A, they are mappings from A to A, right? They should be endomorphisms of the additive group. That's what these two identities about distributivity amount to. That's what a ring is. It's a set together with two special elements. Actually, sometimes those two elements can be the same, in which case it can be checked that every element is equal to that element, whether you call it 0 or 1. Usually it's called 0. If 0 is equal to 1, then every element in the ring is equal to 0. So it just consists of one element. But in general, you have distinct elements 0 and 1. 0 is the neutral element for addition. 1 is the neutral element for multiplication. Under addition, it's a commutative group. Under multiplication, it's a monoid. And addition and multiplication are compatible or distributive over. One is distributive over the other. Now, when you have a ring and you have another ring, A and B, you have two rings, a mapping from A to B is called a morphism or a homomorphism of rings if it takes sums to sums, products to products, and 1 to 1. Of course, you could also say that, you should take 0 to 0 and minus x to minus x, minus f of x. F of minus x should be minus f of x. But that's automatic. If it takes x plus y to f of x plus f of y, then these things are automatic, as in any homomorphism of additive groups. Okay, so the basic example of a ring is the endomorphism ring of a commutative group. You take any commutative group, and there are hundreds of them, infinitely many. I just gave maybe one or two examples, Z and okay, so you all know perhaps many examples of commutative groups. For each such group, you take this of all endomorphisms, and that is a ring. Okay? So the trivial example is the 0 ring, and the basic example is the ring Z of all integers, positive, negative integers. So you have addition, multiplication, you have all the properties required for it to be a ring. So that's a basic example, and in a certain precise sense, that's the first example. It's called the initial ring in some context, but let's not worry about that. Okay, I mean, I could here would be an exercise. So I've told you what a ring is, and you know the ring Z of integers, and I've told you what a homomorphism of rings is. So you try to find out if there are any homomorphisms from Z to some other ring. Actually, there is always a homomorphism from Z to any other ring, and there's a unique one. Okay, so that I'm leaving it to you to check as an exercise. Okay, so now let's go back to this example of a ring, which is the ring of endomorphisms of a commutative group, right? You have a commutative group, you have the ring of endomorphisms, but that ring doesn't come alone. It comes with a mapping. It acts on M in the sense that, why did it become smaller? Anyway, yeah. It acts on M in the sense that there is a natural mapping from end M cross M to M. What is that mapping? It takes an endomorphism F and an element X to the value of F at X. So that's a mapping from end M to M. And you can check, it's not at all difficult, that this mapping, on the very first slide, we had called such a thing an external law of composition. Here the main set is M, and this auxiliary set which we had, it was called omega there on the first slide. This is NM here, and we have a mapping from omega cross M to M, omega being this ring here. You can easily check that this mapping here satisfies these conditions. So f of x plus y is f of x plus f of y. Why is that true? That's true simply because f is an endomorphism of M. F plus g of x is f of x plus g of x. Why is that true? That's true because that's how f plus g is defined. It's defined so that its value at x is the value of f at x plus the value of g at x. Similarly, fg of x is f of g of x. That's how it's defined. The multiplication is the composition of mappings. And 1 of x is x. That's true because 1 is actually the identity mapping of M. So this is nothing mysterious about it. These are all very obvious conditions. So now, instead of this ring and M, let's come to an arbitrary ring. So A is now an arbitrary ring. A module over A, or a left module to be more precise, is a commutative group M together with a mapping, an external law of composition with operators in A, and it takes elements of M to themselves under the operation of this capital, if this ring A. So alpha comma x goes to alpha times x. That's how it's written. And these alphas the elements of A are sometimes called scalars, and the elements of the group M are sometimes called vectors. But wait, they'll be called scalars and vectors once this mapping A cross M to M satisfies these 4 conditions. And these 4 conditions are exactly as the 4 conditions I had here in this particular case of a ring, which was the endomorphism ring of a commutative group M. Now, my ring is an arbitrary ring, and my group M comes with a map. If I have a mapping from A cross M to M, satisfying exactly the same 4 conditions as before, then I say that M is a left module over the ring A. Okay? And you also have the concept of a right module, where you write the scalars on the right on the right. And these 4 conditions translate as these 4 conditions. Of course, the only difference is in the third condition, it says that if you multiply by beta first and then by alpha, it's the same as multiplying by alpha beta. But here you are multiplying by alpha first and then by beta. That amounts to multiplying by alpha beta. So that's the difference between a left module and a right module. Of course, this difference between left and right disappears if your ring A is itself commutative, which means that its multiplication is commutative. But let us, in the first 3 lectures, nothing will change by assuming that the ring is commutative. So we work in this slightly greater generality of of an arbitrary ring, which may or may not be commutative. And when when we say a module over that ring, we will always mean a left module. This is just in order to fix ideas. The same theorems, of course, hold for right modules. It's easy to translate things back and forth. Okay. So maybe I'll just introduce morphisms of modules, and then I'll stop for a minute or two to ask people if they have any questions. Okay. So now, you see, when you talk of morphisms of modules, your ring A is fixed. You have some ring A, and you have two modules, E and F, over that ring. They're both left modules. Now all the modules will be left modules. So a morphism of modules is a mapping U from E to F. It should satisfy two conditions. First of all, it should be a morphism of groups. E and F are, of course, groups to begin with. Before being modules over the ring A, they are commutative groups for addition. So this U should be a morphism of additive groups, which means that U of X plus Y should be U of X plus U of Y. And the second condition is that it should be compatible with the action of A, of the ring A. Which means that if I take an element alpha of A and multiply some element X of E with it, and then apply U to it, take its image under U, I should get an element which is alpha applied to U of X. Okay? So in some sense, this alpha should come out as here on the right-hand side. Or you could say that this commutes with the action of A. Then you say that this U is a morphism of left modules or left A modules. Now, examples of morphisms are very easy to give. The identity map is always a morphism of rings, no matter what. No, we are talking about morphism of modules. So the identity map of E is always a morphism of any A module E. Similarly, if I have three A modules E, F, and G, morphisms of A modules are also called A-linear mappings. Okay, so I'll mostly use the terminology A-linear. That's why it's called linear algebra. It's the study of A-linear mapping. It's the study of modules and these A-linear mappings between modules. So if I have three A modules E, F, and G, and a morphism or A-linear mapping from U from E to F, and another A-linear mapping V from F to G, then I can compose them to get a mapping from E to G, which is written V composed with U. And the point is that this mapping, this is not just a mapping of sets, it's also an A-linear mapping. Okay, so that's also very easy to check. These are all very little things which, so, if you already know this word category, and I used it on the first slide or second slide, so in this sense, these modules over a given ring form a category. Because these sort of, in a category you have objects and morphisms between objects. Here the objects are the A modules, and the morphisms between these objects are simply A-linear mappings. So here, at least after 10 slides, I've been able to define linear algebra, and which is the study of modules over a given ring. Okay, so it's a first approximation to a definition of linear algebra. Let me stop for maybe 1 or 2 minutes to ask if people have any questions. Yeah? Hello? Yeah. Can everybody hear me?
On page number 3.
Sorry?
When we define on page number 3, when we define random modification ring.
I can't hear. Oh, somebody's saying something, but I can't hear him.
Am I audible?
Yeah, very, very okay. Try again.
On page number 8, where you define the random modification ring.
Well, I'm sorry, I can't really hear you. So if you can write it in the chat, maybe I'll be able to read it and reply to it. Are there any other questions? Okay, if not, let's continue. And since I should stop at 6, but I started maybe 10 minutes late, Dr. Gupta, right? So with your permission,
Yes.
I'll continue.
Yes.
Is
Yes,
that
sir.
fine?
Okay, sir. Yes, sir. It is fine.
I just have 5 slides more. So here it is. Okay, so this was just a definition of what a module is and what an A-linear mapping is. Here is a very basic concept, which we will be using this terminology all the time. That's the notion of a family of finite support. So that makes sense of a family of elements of a set when that set has some special element. Let's think of a group which has the unit element. That's a special element. And when we have a ring A, we have the 0 element, which is a special element. So a family of elements, everybody understands, right? A family of elements S alpha indexed by a set I is just a mapping from I to S. Now, this mapping, in the case of a ring, will be called a family with finite support if all S alpha are equal to the special element with only finitely many exceptions. So support is where your mapping is different from 0 in some sense. And finite support means there are only finitely many places, finitely many indices in I where S alpha is different from 0. Why do you have these families of finite support? That's because if you have such a family in a ring, then you can add all the elements. If you have an arbitrary set I and an arbitrary family indexed by I of elements of a ring, you cannot add those elements. You cannot talk of the sum of that family because you have no notion of taking the sum of infinitely many elements of a ring. But you might have infinitely many elements, but only finitely many of them are different from 0. Then, of course, you can say that, okay, yes, I can take the sum of these infinitely many elements. It's just the sum of those finitely many ones which are different from 0. So that's a very general concept. It has nothing to do with modules and so on, but let's now come back to modules. And a very basic concept in a module is that of linear combinations. So what you have is a ring A and an A module M. And you have a family of elements X iota in I, indexed by some set I of this module M. A linear combination of this family is any element which can be written as for which there's a family of finite support of elements of A. So lambda iota in the same I, such that when I multiply these lambda iotas with X iotas for every iota and take the sum, I can take the sum because almost all these lambda iotas are 0, so almost all these terms are 0 only finitely many of them are different from 0. So I can take the sum, and any sum which I obtain in this manner is going to be called a linear combination of this family. So what is a linear combination of this family? It's an element of the same A module M, from which this family is taken, which can be written as the sum lambda iota x iota for some family of finite support lambda iota. That's it. So let us not talk about arbitrary families. Let's just take two elements, x and y in M. What is a linear combination of x and y? It is every element which can be written as alpha x plus beta y for some alpha and beta in A. That's a basic example of a linear combination. So if you have three elements, x, y, and z, of course, a linear combination is any element which can be written as alpha x plus beta y plus gamma y, gamma z, where alpha, beta, gamma are in the ring A. Excuse me. So now, if I have a linear combination alpha x plus ax plus by of x and y, let's say, but x and y themselves are linear combinations of some other elements. Then suppose x and y are linear combinations of z and t. So x is cz plus dt and y is ez plus ft, where c, d, e, and f are in the ring A. Then you can just work it out and see that this element on the left is also a linear combination of z and t. So this can be summarized by saying that if I take the linear combination of some things which are themselves linear combinations of other things, then the final product is a linear combination of the initial things. Okay? And here is one important property of linear combinations. If I have a linear map F from my module, so this linear combination alpha x plus beta y is taking place in the module F, module M. And if I have a little f, which is an A linear mapping from M to some other module N, then F applied to this linear combination is again a linear combination, but here of f of x and f of y. So f of alpha x plus beta y is alpha times f of x plus beta times f of y. Or the image of a linear combination by a linear mapping is a linear combination of the images of the things of which this thing was a linear combination. Okay, so how does one verify this? These things follow blindly from the definitions. You just apply the definitions and you get the result. So earlier we had the notion of a subgroup of a group, right? And I didn't mention the notion of a subring of a ring. But let's talk about the submodules of a module. So if you have a ring A and an A module, oh goodness. Okay, so I have to be really fast. You have an A module E. A submodule is a subgroup of E, subgroup F of E, such that alpha times X is an F whenever alpha is an A and X is an F. Okay, so in other words, if you have two elements in a submodule, then every linear combination of those two elements is again in the submodule. Okay, and here is something which is not very difficult to check, that if you have a linear mapping between two A modules, E and E prime, it's an A linear mapping, and if I have a submodule F in E, and I take its image under U of F, that's going to be a subset of E prime, but I'm claiming that it's actually a submodule. Similarly, if I have a submodule f prime of E prime, I can take its inverse image, U inverse of f prime. That's a subset of E, and the claim is that it's actually a submodule. All these claims are very easy to verify. They follow from the definitions. Okay. Yeah, so here I've tried to indicate why it's a subgroup and why it's stable under, etc. So I've tried to indicate the proof of the first claim. Now, there's this notion of the submodule generated by a subset, which is you have a ring A, you have an A module E, and you have a subset S of this A module E. Now, there are two things which you can do. The first thing you can do is take the set of all linear combinations of elements of S. The other thing, so that's the thing here on the right, the set of all linear combinations of elements of S. The other thing you can do is take all submodules of E which contain S and take the intersection. Of course, this intersection is not empty because this A module E contains S. So you take the intersection of all submodules of E containing S. And my claim is that this intersection is really the same as the set of all linear combinations of elements of S. Okay? So there are, of course, you have to show that this set is contained in this one and this is contained in this. And both of them are rather easy to show because right, a linear combination of elements of S is going to be contained in every submodule, and it is itself a submodule, so the two notions coincide. And the final thing I want to introduce today is the notion of a quotient module, which is when you have a module and a submodule, then of course you can form the quotient group, because this module E is in particular a group and this M is in particular a subgroup. So you can form the quotient group E modulo M. But this quotient group, which is commutative of course, can be made into an A module in a very natural manner. What do I mean by that? I can try to multiply a scalar alpha with an element x bar of E modulo M by putting it equal to, I can multiply alpha with x, of course, because E is given to be an A module, and so I can multiply elements of E by elements of A. So alpha x makes sense, and then I can take its image in E modulo M. But before you can define such a thing, you have to verify that if x bar is equal to y bar, then alpha x bar is equal to alpha y bar. And that's easy to verify because x bar equals y bar means that x minus y is an M. M is a submodule, so alpha times x minus y is also in M. And that means alpha x minus alpha y is an M, and that means that alpha x bar is the same as alpha y bar. So now I can multiply elements of E modulo M by scalars in A. And with that makes E modulo M into an A module, and that's called the quotient of the A module E by the submodule M. Now, here is what is called the universal property of quotients, right? When I make E modulo M into an A module in this fashion, the projection of E onto E modulo M becomes an A linear mapping. I could have also said that there's a unique structure of A module or A modulo M, which makes this mapping pi A linear. And the universal property is that if I have some other A module F and an A linear mapping U from E to F, which takes M to 0, then there's a unique A linear mapping F from E modulo M to F, which makes this triangle commute. And what does it mean for a triangle like this to commute? It means this, that this composite pi followed by F, pi followed by F is the same as U. Take any element X here, apply pi to it, apply F to it, you get the same thing as U of X. Okay, so that's the notion of a quotient module. So that's where I stopped today. I'm sorry that I had to run over time. And next time, Dr. Gupta will set up the, whatever, it's Google Meet session and send us the link so that she can record the thing. Are there any questions? Yes? Somebody had a question, and oh, okay. So on page, where did you define the ring and M? Why did you define the multiplication FG as composition? Why not as pointwise multiplication? Okay. Now, so there's some. Okay, so you see, well, he wants me to go back. So I'll briefly go back to page 8 here. And he said, when I define this ring, he's asking, when I define this ring and M, addition in this is defined sort of pointwise. That's true. But he says multiplication, it was not on page 8, it was earlier, right? It was on page 6. Yeah, so multiplication is defined by composition and not pointwise. That pointwise, it would not be a very interesting structure. Pointwise, one law. So pointwise doesn't make sense. Yeah, okay, so I'm finished. Any other questions? Rahul Arora, if you send me your email address, I'll explain it in an email to you if you have not yet understood what I said just now. So let's stop for today. Okay. Right, Dr. Gupta, shall we close the session?
Yes, sir.
Okay.
So, clap for Professor Dalawat for a nice lecture, well presented in a 1 hour span of a time. Thanks, Professor Dalawat.
Thank you. Thank you.
Thank you, sir.
Okay.
Thank you, sir.
Thank you, everyone.
Yeah. Okay. Thank you.